In this lesson, we are going to learn an alternative method for plotting points called polar coordinates. The traditional system that you use is called the Cartesian or rectangular coordinate system, in which you have the x and y axis, and a point is assigned an x, y coordinate where x is how far over and y is how far up or down. How polar coordinates will work instead is that you have the polar point called the origin and a directed ray, and then every point can be described as a distance r and an angle of rotation theta measured counterclockwise from the what's called the polar axis. So with that, let's plot some polar points. So fix a point O called the pole or origin. So there's my point O. And construct a ray from O called the polar axis. So there's the polar axis. Each point P is assigned a polar coordinates r theta as follows. R is the directed distance from the origin to the point P. So that is R. And theta is the directed angle measured counterclockwise from the polar axis to segment OP. So plot these points. So we have our polar axis and our origin O. Now 3 pi quarters is right over here, and this should have a distance of 1, or a length of 1. So there's the point 1 comma 3 pi over 4. Now the point 2, 3 pi, here's the origin, here's my polar axis. So 2 pi would be 1 full rotation, and an additional pi puts me over here, and from there we have a segment of length 2. So there is the point 2, 3 pi. Notice that a simpler way to express that would have been 2 pi. Now this is one difference between polar coordinates and rectangular coordinates. Rectangular coordinates are unique. If I give you an x comma y, that is 1 point. But if I give you an r comma theta, there could be a different r theta that represents that point. Alright, 2 negative pi thirds. So here's my origin, there's my polar axis. Instead of going counterclockwise pi thirds, I go clockwise pi thirds. And the length of that should be 2. And this angle should be theta equals negative pi thirds. So this is the point 2 comma negative pi thirds. Now the next question is what to do when you have a negative radius. Like, how does that work? So how this will always work is you plot the point that is 2 comma pi quarters, and then you reflect. So I'll show you what I mean by that. So here's my origin, there's my polar axis. The point 2 pi quarters is right there. Now to graph negative 2 pi quarters, we reflect or continue that line in the sort of negative direction. And that's the line right there. Length of 2, so there is the point, negative 2 pi quarters. A way to express that without the negative 2 would be a radius of 2 and an angle of 5 pi quarters. Now the point negative 2 negative pi halves. There's my origin. So I go down, or backwards, like clockwise, pi over 2, and then I reflect that up, which makes this point. So there is the point negative 2 negative pi halves. And another way to express that would have been 2 comma pi over 2. And then to graph negative 3 negative pi 6, have our polar axis, go backwards pi 6, and then reflect and the length of this segment should be 3. Next question, is the polar representation of a point unique? If not, give 3 different representations of the point 1 comma pi quarters. So it's pretty obvious from the previous examples that there's more than one way to represent a point. So, for example, the point 1 comma pi quarters, that would be the point. So it has a distance of 1 and an angle of pi over 4. But it would be the same point if you did 1 comma pi quarters plus 2 pi. So 2 pi is 8 pi quarters. That's the same thing as the point 1 comma 9 pi quarters. So that's one other representation. Another representation is you could go clockwise instead of counterclockwise, in which case you'd have 1 comma negative 7 pi over 4. And if you want to get real fancy and make a negative radius, you need to get to this point so that you can reflect. So that would be negative 1 and the angle 5 pi quarters. Or if you want to be an overachiever and get one more point, you could have had negative 1, negative 3 pi quarters. So there are an infinite number of ways to represent a point in this system. The next question to address is how does this system relate to the system that you sort of know more thoroughly? How does it relate to your Cartesian or rectangular coordinate system? So if we have an angle theta, we have this polar coordinate point r comma theta, where r is this distance. So that distance is x, this distance is y in the regular Cartesian system. So then using trigonometry, we know that cosine of theta is equal to adjacent over hypotenuse, and solving that for x, we get that x is equal to r cosine theta. And we also know that sine of theta is opposite over hypotenuse, which tells us that y is equal to r sine theta. So this would be used to go from polar into Cartesian. Now to go the other way, we have that tangent of theta is equal to x over y, which also comes from trigonometry, as we find an angle that satisfies this relationship. And using the Pythagorean theorem, you can see that r squared is equal to x squared plus y squared. So now that we understand these relationships, let's do some conversions. So let's convert 2 pi 6 into rectangular coordinates. So in this case, x is equal to r cosine of theta, and y is equal to r sine theta. So x would equal 2 times cosine of pi 6, and cosine of pi 6 is root 3 over 2. So the x-coordinate of this point is root 3, and the y-coordinate is 2 times sine of pi 6, and sine of pi 6 is 1/2, so 2 times 1/2 is 1. So the rectangular coordinates at this point are root 3, 1. Now the point 1, negative 3/4. Once again we have x equals r cosine theta, y equals r sine theta. So x would equal 1 times cosine of negative 3 pi over 4, and y would equal 1 times sine of negative 3 pi over 4. And negative 3 pi quarters falls right there if you're using your unit circle as a reference. So negative 3 pi quarters, the cosine is negative root 2 over 2, and the sine is also negative root 2 over 2. The rectangular coordinates are negative root 2 over 2, negative root 2 over 2. Next, let's convert this point to polar coordinates. Convert the following point to polar coordinates. So the point 1, -1 is located in the third quadrant, back 1, down 1. So we want to figure out how to represent that with polar coordinates. So first of all, you know that r squared is x squared plus y squared. So r squared is -1 squared plus -1 squared, or r squared equals 2, which means r is positive root 2. Technically positive or negative root 2, so we're just going to take r equal to positive root 2 to make it a little bit simpler. Now to find the angle, you solve tangent of theta equals x over y. So that would give us tangent of theta equals -1 over -1, which is equal to 1. And the solution for tangent, where you get tangent of theta is 1, which lies in the third quadrant, is for the angle theta equals 5 pi quarters. So the coordinates of this point in polar coordinate form are root 2, 5 pi quarters. And because this representation is not unique, that is not the only way to express this point, but that probably is the simplest one. Alright, the point 0, 3. This one you can probably do without the conversion formulas. So 0, 3 is the point that's over nothing up 3. Pretty obvious then that the radius is equal to 3, and the angle theta, since that's a quarter turn, in radians is pi over 2. So the point can be expressed as 3 pi over 2. Now technically, WebAssign should take all equivalent forms of a point, but if it doesn't or doesn't appear to, just let me know via some email and I'll check it out and see what's happening. So now that we know how to find graph polar points, let's sketch some polar curves. So let's start with some simple ones. R equals 3. This is a collection of all points which are 3 units from O. So if I have my origin, we'd have 3 units out this way, 3 units out, 3 units out. Pretend like I can actually draw, and that's actually 3 units out. So 3 units out, and then 3 units out, etc. So this will be a circle with r equals 3 centered at the origin 0, 0. And you can confirm that using the conversion things. We know that r squared is equal to x squared plus y squared, and since r is 3, we have 3 squared equals x squared plus y squared, which is the formula for a circle of radius 3 centered at the origin. Now theta equals 1. This will end up being a straight line, which means we have any radius, but the angle is always 1. So 1 radian. Always 1 radian. And if we had the point, say, r was -1, angle theta was 1, we would graph that by going to this point. That was a distance of 1 out, then reflecting, so we also get the line in this direction. So this produces a straight line. Next we have the curve 3 sine theta. This one is not quite as obvious what this is going to be, so we're going to make a table and we're going to plot points. Unfortunately, if you don't know your values of your trig functions, like say from trigonometry, this is going to be a little bit hard. You're going to really have to use a unit circle. So first, if we input 0 for theta, sine of 0 is 0, so my r is 0. So this curve, if this is my O, will start there at the origin. At pi over 6, sine of pi over 6 is 1/2, so we have 3 times 1/2, which is 1.5. So at an angle of pi 6, It's about 1.5. And then plugging in pi quarters and pi thirds doesn't yield very, very nice numbers, but when we plug in pi over 2, sine of pi over 2 is 1, so we get that this is 3. So by there we're up at 3. And by 5 pi 6, sine of 5 pi 6 is also 1/2, so we get the point 3 times 1/2, or 1.5 again. So that's the point over there. And we plug in pi, we're back at 0, and then we're going to cycle again. So what's happening here is we're having a circle, and it looks like the diameter of this circle is 3, which means the radius must be 1.5, and we can verify that. So recall that we had y is equal to r sine of theta. That tells us that y over r is equal to sine of theta. So I can input y over r for the sine of theta, which gives us r equals 3 times y over r, or multiplying the r to the left side would give us r squared equals 3y. And then we know that r squared is x squared plus y squared, so x squared plus y squared equals 3y. And now you have to remember how to complete the square, which is a topic that's taught in some Algebra 2 classes and some pre-calculus classes, but could have been a long time, so we'll go over it. X squared plus y squared minus 3y. Now you add half of that 3 squared. So half of 3 is 1.5. We're going to add 1.5 squared to this side and 1.5 squared to that side. Then we have x squared. This y squared minus 3y plus 1.5 squared factors into y minus 1.5 squared. And that's because 1.5 times 1.5 makes 1.5 squared, and 1.5 plus 1.5 makes 3. And that's the equation of a circle with center 0, 1.5, which is where the circle center appears to be, and a radius of 1.5, which, if the diameter is 3, the radius of the circle should be 1.5. Next, we're going to sketch the polar curve 1 minus 2 sine theta. So I'm going to start by graphing this 1 minus 2 sine theta in rectangular coordinates. So first, negative 2 sine of theta. So sine has a period of 2 pi. You can plot trig functions using what's called the 5-point method. So sine begins at 0. It's 0 again halfway at pi, and it's 0 again at 2 pi. So there we have pi, here we have 2 pi. Now because this is negative sine, it's going to decrease initially. Its lowest value is negative 2, so we have this kind of thing going on. And its highest value is at 2. And you see the 1, 2, 3, 4, 5 points there. So what you have to do first is figure out how long the period is, and then figure out where those 5 points go. And after we have negative 2 sine theta graphed 1 minus that, we'll take this graph and we'll shift it up 1. So now the lowest point is negative 1. The highest point's at 3. So this point that was on the origin's now at 1. At pi over 2, we're now at negative 1. At pi, I'm actually at 1. At 3 pi over 2, I'm at 3. And at 2 pi, I'm back at 1. So that's a rectangular graph of 1 minus 2 sine theta. And let's just figure out what these intersection points are. So when does 1 minus 2 sine theta equal 0? which means 1 equals 2 sine of theta, which means sine of theta is a half, and that happens when theta is equal to pi over 6, which makes sense. That point right there is somewhere between 0 and pi over 2, and that's also true at 5 pi over 6. Alright, now let's use this to graph the polar curve 1 minus 2 sine theta. So we start, this is the theta axis and this is the r axis, with this point right up here. When theta is equal to 0, I have a radius of 1. So I start over there a distance of 1 away from my point O. And then as I continue along this portion of the curve, as I go to the angle of pi 6, my radii decrease. So that's going to look something like that. Now for this, let's look at that particular point there. For that middle portion there, by pi over 2, so at an angle of pi over 2, I have a radius of -1. So I would graph that by going pi over 2 up 1, and then reflecting that point down. So by this point in time, I've gone through and done this kind of thing. And then this next portion, continue back up to 0. Now from there, at the angle of 5 pi 6, I'm back at a radius of, actually that's wrong, by this corresponds to pi. By pi, I'm back at a radius of 1. And then from there, new color. Okay, next, by 3 pi over 2, I have a radius of 3. So the angle 3 pi over 2 is down here, and that was 1, 2, 3. So by then I'm down to there. And for the remainder of the curve, as the angles decrease, the radii decrease back down to 1. So there is a graph of the polar curve 1 minus 2 sine theta. This is just a convenient way to represent the r's and the thetas so that you can graph them. It is not a graph of the polar curve, it's a graph of the rectangular curve. So you're going to need to draw the curve using the radius angle definition, not the over-up definition. This is the tool to help you do that. Next, let's sketch the curve r equals cosine of 2 theta. So first let's figure out what the period of cosine 2 theta is. So 2 theta equal to 2 pi when theta equals pi. So this curve will go through one oscillation in pi. So using the 5-point method, that period of cosine 2 theta ends in pi, making this point pi over 2 and those points quarters. Now cosine, since it's just cosine of 2 theta, well, cosine of 0 is 1. The next point will be 0. By pi halves we're down at -1, back up at 0, and then back up at 1. Let's graph one more iteration. Oops. There's 3 pi over 2, and there's 2 pi. Back at 0, by 3 pi over 2, we're back at -1. Back up at 0, ending up back at 1. And we're going to use this to graph the polar curve. Okay, so we start, so this is the theta axis, this is the r axis. We start with theta equal to 0 and a radius of 1, so there's our beginning point at 1. Now for this first curve, once we get to theta equals pi quarters, so at this sort of diagonal right there, the radius has gone down to 0. So there's the first portion of the curve. Now this next bit, first let's graph that point. So that's the point -1 pi over 2. So to graph that, you would go up 1 and then reflect down. So what has to happen on that portion is it goes like this. Next, let's graph this bit. So by the angle, that would be 3 pi quarters. We're back at 0. And those radii were negative, so they reflected over into that fourth quadrant. Next, let's do the more straightforward portion there. Okay, so we have by pi, we're up at 1, so that will put us over here. And then by the time we are at, I guess that would be bigger than pi, 5 pi quarters, we're back at 0. So there we go. And that keeps going. I'm running out of colors. Okay. So by 3 pi over 2, that's the point -1, 3 pi over 2. So to graph that, you would go 3 pi over 2, 1, and reflect it, and that would reflect up. So we'll have that portion there is next. And then next, we go down to the radius being 0 again. And then to finish it off, finally at 1, the radius is 2 pi. So that's called a rose curve. And you have to sort of keep graphing until you notice that the pattern repeats. From this point on, after 2 pi, we'd be back at on the first red bit, so following around in that particular order. Sketch one last rose curve. This one is 4 sine of 3 theta. So first let's figure out what the period of sine of 3 theta is. So if 3 theta equals 2 pi, that happens when theta is 2 pi thirds. So the length of this curve, or the period of this, is 2 pi thirds, which makes halfway pi thirds. Halfway between 0 and pi thirds is pi sixths, and halfway there is pi thirds plus pi sixths, so 1 pi sixth, 2 pi sixths, 3 pi over 6 makes this point actually pi over 2. And now graphing the sine curve, sine begins at 0. By pi sixths, it'll be up at 4. By pi thirds, it'll be back down at 0. By pi halves, we'll be at -4. And by 2 pi thirds, we'll be back at 0. Go through 2 periods just to be safe. So after 2 pi thirds, adding on pi sixths would be 5 pi sixths. And we're back at 4. Then we'd have 5 pi 6 plus 1 pi, be back at pi, where we're going to be at 0. And then we'll be at 7 pi 6, which will be back at -4. And by 8 pi 6 or 4 pi thirds, we're back up at 0. So there is the graph in rectangular coordinates. And now let's use that to graph the curve in polar coordinates. Okay, so we start off angle 0, radius 0. Now as the angle increases to pi 6, the radius increases to 4. So roughly speaking like this, and that distance is 4. And then as the angle increases to pi thirds, so like along this portion of the graph, if I have color you can actually see, along that portion of the graph the radius decreases to 0. So we're going to have that bit next. And the next part, this easy point to plot right there is the one down there, which is negative 4 pi over 2. To graph that we would usually go pi over 2 up 4, but it would reflect down to negative 4. So that will take us over here. Now this next portion, once we're at an angle of 2 pi thirds, will take us up. Now 2 pi thirds lies over in this quadrant, but it's going to reflect over into the fourth quadrant because the radii are negative. So what that means is the curve is going to go back up, back up to the origin, like this. And now from 2 pi thirds to 5 pi 6, between there the radius increases back to 4. And by pi, radius is back down to 0. And from there I think we're going to repeat, so in that direction, then that direction. By 7 pi over 6, that's radius negative 4. 7 pi 6, so we go over 7 pi 6, reflect up 4, that would put us over there. So there is the curve for sine of 3 theta. So now that we can sketch these polar curves, we're going to talk about how to find tangents to them. So we have to go back to the parameterization where we had x is equal to r cosine theta, and suppose we have a polar curve r equals f of theta. So that makes r cosine theta into f of theta cosine theta, and y into f of theta times sine theta. Now, using the product rule, so remember that we had r equals, or sorry, not r equals, x equals r cosine theta, y equals r sine theta. So the derivative of y with respect to x is dy d theta over dx d theta. We did the same thing just with t's in a previous section. So dy d theta, we differentiate y using the product rule. So the derivative of r is dr d theta, whatever that might be, times the sine of theta, plus r cosine theta. And now the derivative of x, so x is r cosine theta, that will be dr d theta cosine theta minus r sine theta. Now, horizontal tangents occur when the numerator, dy d theta, is equal to 0, provided dx d theta does not equal 0. So if the numerator and denominator are both 0, we'll have to be a little bit more careful. And vertical tangents occur when the denominator, dx d theta, equals 0, once again provided that the numerator, dy d theta, not equal to 0. And using that, let's find some horizontal and vertical tangents. Find the horizontal and vertical tangents of r equals cosine theta for theta between 0 and pi. So we need to find an expression for dy dx, which is given by dy d theta over dx d theta. And using our previous results, that is dr d theta sine theta plus r cosine of theta over dr d theta times cosine theta minus r sine theta. Honestly, how I would remember that, I would just remember that y equaled r sine theta and x equaled r cosine theta, and I would just rederive it every time using the product rule. It would be the only way that I could remember it. I'd never memorize those formulas. Now, using cosine theta for the r, dr d theta is negative sine theta, so we have negative sine theta times sine theta plus cosine theta times cosine of theta over cosine theta times cosine of theta. Oops, that's not right. I need to differentiate that. So dr d theta is negative sine. So negative sine theta cosine theta minus cosine theta sine theta. So that gives us cosine squared theta minus sine squared theta over negative 2 sine theta cosine theta. And don't go off and say cosine squared minus sine squared is 1. That's not true. Cosine squared plus sine squared is 1, and you can't just change that minus to a plus because you don't like it. But what you can do is you can factor that into cosine of theta minus sine theta times cosine theta plus sine theta. That's this difference of squares pattern. Usually you see it in an easier form, like x squared minus 4 factors into x plus 2, x minus 2, just that the x is replaced by cosine and the 2 is replaced by sine. And the denominator can't factor, so we'll just leave it as a product. Negative 2 sine theta cosine theta. Now we will have a horizontal tangent if the numerator is equal to 0. So if cosine theta minus sine theta times cosine theta plus sine theta, if that's equal to 0. And we will have a vertical if negative 2 sine theta cosine theta equals 0. Now this first expression, that cosine theta minus sine theta, that means that your cosine and your sine have to be equal. And cosine and sine are equal at theta equals pi quarters and 5 pi quarters. Now the second one will imply that cosine of theta equals negative sine, so they're the same numbers but opposite. And that occurs at 3 pi quarters. Oh, actually, we only care about the interval from 0 to pi, so 5 pi quarters out of the interval. The other solution to the next one would have been 7 pi quarters, but it's out of our interval, so just pi quarters and 3 pi quarters. Now the next expression will equal 0 if either sine or cosine is 0 within the interval from 0 to pi. So sine is 0 at theta equals 0, and also pi, both of which are within the closed interval. Now cosine, that's 0 at pi over 2 and 3 pi over 2. But 3 pi over 2 isn't within the given interval, so that one we do not count. So we have horizontal tangents if theta is equal to pi quarters and 3 pi quarters. And notice how none of those matched up. They were not 0 in the same places. And vertical if theta is equal to 0, pi, or pi over 2. In our final example, we'll discuss how to deal with the problems of the numerator and denominator of that expression for dy dx being 0 at the same time. So let's find the horizontal and vertical tangents to the graph 2 times the quantity 1 minus sine theta. So first let's distribute that 2, write it as 2 minus 2 sine of theta. So recall that dy dx is equal to dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta. And let's input everything. So if my r is 2 minus 2 sine theta, dr d theta will be negative 2 cosine theta. So we'll have negative 2 cosine theta sine theta plus 2 minus 2 sine theta multiplied by cosine of theta all over negative 2 cosine theta times cosine theta minus 2 minus 2 sine theta times sine of theta. And don't go making up cancellation rules. You cannot cancel those 2 minus 2 sine thetas or anything else. You have to simplify the numerator and denominator separately. That's actually the order of operations. That fraction bar acts like a parenthesis holder. So here we go. Negative 2 cosine theta sine theta plus 2 cosine of theta minus 2 cosine theta sine theta. Okay, all over negative 2 cosine squared theta minus 2 sine theta plus 2 sine squared of theta. Okay, combining a little bit here and there, and let's divide everything by negative 2, or by 2, just to make it look a little bit simpler. So I'm also going to, in the same step, combine some like terms. So those two can combine. So we'll have cosine of theta minus 2 cos theta sine theta. Really, they would have added to negative 4 cosine theta sine theta, but I divided it by 2. All over. Now in this denominator, I have a sine, and a random old cosine. So let's put that sine squared of theta first, minus 2 sine theta, and then minus, I can make that cosine squared into 1 minus sine squared theta. And that gives us, in the numerator, we can factor out a cosine theta, 1 minus 2 sine theta. In the denominator, I will have 2 sine squared theta minus, oopsies, this should have been just plain old sine theta because I divided by 2, so that 2 should not be there. Let's get rid of it. Minus sine of theta minus 1. Okay, now factoring a little bit further, my numerator is still cosine theta times 1 minus 2 sine theta. Recall that that denominator was 2 sine squared theta minus sine theta minus 1. Now think about how you would factor 2x squared minus x minus 1. You'd say it was 2x and x, and then you've got to figure out where the negative 1 goes and where the positive 1 goes. So I think if you put the negative 1 there and the positive 1 there, that checks out. 1x minus 2x makes negative x. So that gives us cosine of theta, 1 minus 2 sine theta over 2 sine theta plus 1 times sine of theta minus 1. And we will have horizontal tangents if the numerator equals